we want to find the most likely state sequence given the observed sequence. So I give you the sequence of observed things like words, and I ask you, what are the part of speech tags for this sequence of words? And the other things I give you is I give you the parameters of the model. So I've stopped writing fire, but just remind yourself that it is there. And what I tell you is I also give you the probability. So for example, I tell you what is the probability of going to a verb given that the previous thing was a determiner, and all the other probabilities that you need. And I tell you the probability of outputting the word water given that I'm in the state now, for instance. Okay? This is really captured by my A matrix, and this is captured by this phi matrix, and you're given that. And now I ask, tell me the optimal state sequence. Okay, so I want to find the argument max, in other words, the best state sequence for this probability. Okay, and then you go back to grade 1, you learned Bayes' rule. Okay, so what we're going to do is we're just going to use Bayes' rule. Let me just scribble it out. I actually always forget it. So maybe I shouldn't be so condescending. I always have Wikipedia open to tell me what Bayes' rule is. AB divided by P of B. So this is my A, and this is my B. Okay, and then I can write it out like this. Okay, so I've got P of A given B. Here I've got P of A and B divided by P of B. Okay. Now the cool thing is, because we're looking at the maximum, and the maximum is over what? My state sequence. There's no x in here. So for whatever state sequence I pick, it's going to have the same P of the same marginal probability at the bottom. So because I'm taking the max, I can chuck that away. P of x is the same regardless of the option that I'm choosing through my graph. Okay, so I can chuck that away, and I end up with the P argmax, this, and then I've got the joint probability here with a specific setting of the observed state sequence. What we could do is, if I give you P of x1 to t, and I give you the state, well, we don't know the state sequence, okay, but I give you P of x of 1 to t. What I could do is, I could just say, okay, I've observed the specific sequence of words. Let me go through the state diagram in one way. Let me go through it in another sequence. Let me go through another sequence. Let me go through it in another sequence. And I just consider every possible way to make a pass through the state diagram. Every possible way. And I keep track of this probability for that path. And that's actually quite simple. I'm just multiplying probabilities together, okay, as I'm moving through. And then what I do is I just go through all the possible paths through my graph. I pick the best one, and then I've solved this problem. I found the best way to get through the graph. Let me say that again. So let's say I've observed a sentence, a cat drinks water. Okay? Then one way to go through this graph is to say, okay, well, start the sentence, a cat drinks water, end of sentence. That was one path. Okay? And the cost of that path would be so I pay, well, not the cost, actually the score. So when I say I do a cat drinks water, end of sentence, then the score that I would get for that path is the probability of verb given sentence, which I have noun given verb output, determiner given noun output, verb given determiner output, and then end of sentence. Okay, and so you would have the probability for that specific sequence. Okay. Now what we want is we want the best probability of moving through this graph. And one way to get that is to consider every possible way of getting through this graph, store the scores for each possible way, and then you tell me, listen, Herman, the one that has the highest score is this path, go on with life, this is your part of speech sequence. What's the problem with this approach?
There could be a lot of states.
There could be a lot of states, but more importantly, you're right that is the problem, there's going to be a lot of paths. How many paths are there? We have a sequence of length t, okay? And let's say there's k possible states. How many paths are there? Okay, don't guess, just know, right? No. Okay, let's think through this. Okay, so we've got the start state, the end state, and then there's k states here in the middle, capital K states in the middle. And we're trying to process a sequence with t stuff, okay? So when we start here, how many options do I have? K, that's right. I've got K options that I can move to. Okay, so now I move into this thing. How many options do I have from this state to all the other states? How many? Okay, you guys are slightly confused. Like I am K minus 1, maybe K plus 1. I'm not sure, but in the order of K. Okay, you're not wrong. Okay, so now I move to the next one. Okay, how many options? K. Okay, times K. And dunk, 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 dunk. And how many Ks do I have in that list? Exactly. So you've got T of these Ks, and there's T of them. So roughly, I mean, this is just you put the O here because then you can fudge things up, right? So roughly in the order of K to the power T possible paths. Okay, now if you're doing speech recognition, K is maybe 5,000, okay? And T is, I mean, it can vary, but let's say 100, okay? So 5,000 to the power 100. Many possible paths, pain, suffering, like sadness, everything all glued in there. Okay, cool. Okay, so how do you solve this? Can you remember that with edit distance you had a similar problem? That you could align these sequences in a ton of different ways and you need to pick the best alignment. But you didn't want to explicitly consider all possible alignments. Instead, you did something else. As is the case with edit distance, if you've watched that video, what we're going to do is we're going to use something called dynamic programming. And dynamic programming, what that means is I'm going to simplify the problem so that I don't have to look at my entire history of everything else that's happened on Earth before. And I'm just going to isolate things so that I have a simple problem that I can solve locally, which then gives me the alignment optimally for the whole sequence. Okay, and the algorithm, in this case, the dynamic programming algorithm for finding the best sequence through a hidden Markov model is called the Viterbi algorithm. But it's going to look very similar to what we saw with edit distance. So what I'm going to do is I'm going to derive the algorithm and then I'm going to do an example. Okay, and then we see what happens after that. To do this, we're going to define our little solve problem, and hopefully that little solve problem we will be able to solve without looking through our entire history of everything else that's happened before. So we're going to define this probability, and it's called delta Tj. Okay, and what is this? So this is the probability of being in state J after seeing the first little t observations and passing through the most probable state sequence up to that point. This means that I am looking at the probability here of basically ending in state J. That's the state, the label for the state that we're given. Okay, and up to that point, we've moved in the best way that we could. We followed the best path up to this point. Okay, and that's why you have that max there. So we've followed the best possible path up to this point after observing the first little t, basically emissions, the first little t observations. Okay, so we're kind of in the middle of our sequence somewhere. Okay, we're at time step 10. And what this says is, what's the probability of being in the specific state J, given that up to time step 10, well, actually up to time step 9, we've moved optimally, and that I've observed the first 10 outputs. Okay, up to, it's not really up to that point, it's up to the time step just before it. Okay, so basically Z0 to t minus 1 has been the best possible way to get to that point. Okay, is everyone with me? Okay, now this is our little sub problem, and what I will show you is that if you can figure out a way to get this, to get these probabilities out, if you've solved that, then you've reduced things to a little small problem that I can look at locally, and that will allow me to figure out how to get the best optimal assignment globally through the through my little state machine. Okay, now get ready for some math. Is everyone ready? I was born ready. What we're going to do here is we're going to repeatedly apply the chain rule of probabilities. Okay, chain rule. Okay, these are one of these rules that you learned in grade 1, but you might have to look up every now and again. Okay, So it says that the joint probability of A and B is equal to the conditional probability of A given B times the probability of B. And we're just going to apply that repeatedly in order to come up with the equation that looks more simple than this. And the equation we will end up with is that equation at the bottom there. Okay, cool. So what we do is there's a bunch of random variable stuff in here, and I'm going to slice off parts of it repeatedly by treating it as A and then the rest as B. Okay. So the first thing that we're going to treat as A is I'm going to treat xt as my A, and then I'm going to given, and then there's all the rest of the stuff. Okay, so this is like my A, and then all the rest of the stuff goes here. Remember this is a sequence here, right? And what I've done is I've split off the very last thing in that sequence. So what's left? Well, all the rest, t minus 1, and then z0 to t minus 1, and then zt is equal to j, and all of that thing is my b. Okay, that's a little bit frustrating. Okay, but then we end up with p of b intense. Can I simplify this? Quickly tell me what this is. Okay, let me tell you what this is. So this is the probability of outputting something given everything that came before it in the sequence and all the states before it and the current state. Now, what do you know about a hidden Markov model? If I'm outputting something, what does that depend on? Almost, not the previous state. When I'm outputting something, it only matters what happens in this state right now. Given that I know I'm in the current state, what does this stuff do? It doesn't matter at all. So this can be simplified, and I can do p of xt given just what state I am at time step t. None of the other stuff matters. And now what we do is we apply the chain rule again to this part. And what I'm going to do here is I'm going to treat this part as A, okay, and then all of this will be my B part, okay. So we do that again. So here we've got P of ZT J given the monstrosity that follows t minus 1, Z0 to t minus 1, okay, then times, and now I need my P of B. So I've got P of x1 to t minus 1, Z0 to t minus 1. Okay. Okay, let's go on. I want to get things simpler, but it looks like I first need to make things more complicated. Okay, but we'll get there. And stare at that thing, tell me how to make it simpler. Okay, so let me tell you what this is. So this is the probability of being in a current state given everything else that got out of my model before, and given all the previous states that I've observed before. So what do you know about a hidden Markov model? What you implicitly said is that you don't have to look at all the previous states that came before it and all the previous stuff that came out. All I have to look at is what state was I in the previous time step. That's the only thing that matters. Given that I know what happened just in the time step before it, so basically just at t minus 1, it's conditionally independent of all of the other stuff here. So I just have z t minus 1. Okay, and let's spoil it. This is that matrix A. So it tells you how to go from that state into that state. Okay, and then we still end up with this last little density here. And we're actually almost done. I'm just going to now do something a little bit weird, and then you'll see that why this works out. So I'm just going to divide this max at the front into two maxes. The max from Z0 to t minus 2, and then I'm going to do a max. And for the state just before the state that we're looking at now, the t minus 1 state, I'm just going to explicitly iterate over all of those states. Okay, so there are capital K states, and zt minus 1 is now either 1, 2, 3, 4, 5, or capital K. Okay, this will make sense in a second. So we've got P of x t given zt is equal to j times P of zt is equal to j given zt minus 1, and zt minus 1 is now basically coupled to that k because I split it off from that sequence there. So zt is equal to I, okay, times p of x 1 to t minus 1, z0 to, and now I'm just going to explicitly write zt minus 1 on its own is equal to I. Now I end up with that. Yeah. Okay. Is everyone with me? Then what I'm going to do is, let's just check this. Z0 to t minus 2. There's nothing involving it here. Z0 t minus 2, there's nothing about that there. There is stuff about it there. So what I can do is I can move this max and I move it right there. Okay? And we'll see in a second why we do that. So now we end up with a little equation here of p of xt given zt is equal to j times, okay, cool. Now we can just replace this thing. That is the transition matrix. So that is the probability of going from state I in the time step before to state j in the time step that follows. Okay, times, and now we've got the max z0 to t minus 2 of this monstrosity that is left over. Oh, okay. Now, why has this simplified things? Look at that definition here. And then look at that thing that we have there. That definition here. And then this last bit here. Let's make it in red. The red part there. And that definition. And what can you tell me? It's almost the same. There's a t minus 1 there. There's a t minus 2 there. There's a t minus 1, there's a t there, there's a t minus 2, a t minus 1 there, and there's an I there, and there's a j there. So actually, if you make t minus 1, and you make j I, then this red part is exactly that part there. Okay, so this red part is, you can write it as delta t minus 1 I. If you replace all the t's with t minus 1 and all the j's with i's, then you end up with exactly that thing. And so what we've done is, so if this red part is that, then you can take that and stick that in there, and we end up with a little equation here that looks like this. And the nice thing about that equation is we managed to get a recursive equation for this delta t thing. Okay, we managed to find an equation where we use previous versions of delta t in order to calculate it, and that allows us to not have to go through all of the previous steps when I'm trying to figure out what to do right at this time step. Remember, what we're actually interested in is basically we're trying to figure out the best overall path if I've got an observed sequence through this state diagram. Actually, if you go through similar steps with the delta, then you can actually show that the best overall probability through the graph would be given by this equation. Okay, now what the fudge does that mean? So it basically means we calculate these delta tj's or delta ti's. We calculate that for all the time steps for all the states. And once you've done that, you end up with a ton of these deltas. But that allows you to tell me how to get the best overall score for getting through this graph. After you've calculated all of them, the last step that you need to make is you need to move to the last state in your diagram. Okay? The end of sentence state. And what this equation tells me is, what I need to do that is I calculate delta for state 1 at time step t, the last character. I calculate delta for time step t, the second state, delta for the last character or the last output for state 3, and so on for all the other states. Okay? And then what I do is I basically say, okay, well, to get to the end state, I have to pay that last transition probability from state 1 into state k plus 1. I need to pay the last transition probability from state 2 to state k plus 1, and so on. A state 3, k plus 1. Okay? And what I do is I take the maximum step over all of them. The maximum, the one that has the best score, I pick the one that works the best. Oh, this is the crucial part. This is a crucial part, so just pay attention now. Okay? What this little algorithm allowed us to do is, remember, we want to get the best way to get through this machine, this state diagram. Okay? We always end where? In that very last state, in the end of sentence state. That's always where we end. To figure out the best path, what we do is we say, okay, cool, we've ended in this state. To get to that state, I had a few options. Okay? I actually had capital K options. In the previous time step, I could have been in state 1, or I could have been in state 2, or state 3, or state blah, 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 whatever state. The best way to get to that state is, well, my one option is to move optimally until I get to state 1, and then take the very, very, very last step to the end of sequence. The other option I had was to move optimally in some way until I get to state 2, and then take the very last step. Move optimally, end in state 3, and then take the very last step. Okay. Now the best overall way would be to say, well, I moved optimally here, and then I take that little step. That's one option. Move optimally here, little step. Move optimally here, little step. The globally optimal way would be whichever one of these options is best, and that would be the best state sequence. Okay, that would correspond to the last step in the best path. Should I say that again? What do I have to do in order to find the best overall path is I just need to look at the states that came just before me. So the best path in the whole thing would lie here, 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 or here. Which one do I pick? The one that's the best option out of all of these options. And the best option is basically move optimal to this point and then take one step. Move optimal to this point, take one step. Okay? And then if I incorporate these steps, then the best overall score is going to be the one that's the best out of these options. Okay? So when I'm backtracking, that basically says like, okay, let's say this path, this one, is the best path in this max operation. Okay, cool. Now I'm sitting here, and this state is connected to a whole bunch of other states. Okay? And now what I do is I ask, well, to get here, what was the best previous step that I made? Oh, it's this one, and I take the red route here. Okay, cool. Now I'm in this state, and then I go back again, and back again, and back again, and that gives me the best overall path. Okay. If that doesn't make sense, just hang on, because I'm going to actually do a full example with actual values for a little hidden Markov model, and then that should make sense. But I hope the idea of breaking it down into these subcomponents are clear to you guys. I might have lost some of you with the Viterbi algorithm, but when we're doing an example, it's going to be clear, and that's what we're going to do in a second. Before that, just a summary of the whole algorithm. The crucial part is really this recursion, where you're using previous versions of these deltas in order to calculate the delta that I'm currently interested in. And the crucial thing is, in the inner loop of this algorithm, what you're going to do is, for every time step that I'm in, for every one of the observations, I'm going to calculate a delta, and this delta is basically a function of the state that I'm in, so I'm going to calculate this for every one of the states. Let's make a concrete example. At time step 10, what is the chances of being in state 5? Okay, in time step 11, what's the chances of being in state 4, 3, and so on? Okay, so we're going to calculate that in the inner loop. There's a little bit of a formal notation here. You've got this, I don't know what this thing is called. Psi, is that right? But the equation looks exactly the same, except it has an argmax. So what you're doing here is you're just keeping track of the best option that you took when you went into a specific state, so that when you backtrack, you can just look up that option in order to find the best path through the state sequence.